Today we will see about bandpass noise. First of all, I would like to tell you what is noise. What is noise? Noise is a signal. I can say noise is a signal which occurs randomly. What is the meaning of this randomly occurring? How does a signal look like? How can we represent a noise? Those are the point of study in this lecture. One can say that noise is a random signal. What is that random signal? Both amplitude and frequency to be random. That's called as noise. Suppose if I draw a noise is something which looks like this, where you have both amplitude and frequency varies, phase, everything varies. Definitely, this may not be so periodic like this. You may have a mixture of all the frequency and it randomly comes. Can you see what's happening in this? This is a noise. If you see the characteristics of the signal, see what the signal characteristics, amplitude and its frequency, right? And you can see this particular signal has both amplitude and phase variation. Can you see here? Or frequency variation. Right? This is a random signal. If we talk of from signal point of view, this has both amplitude and phase variation or frequency variation. That means it has an infinite amplitude and also infinite frequency. It has all frequency components. If this noise has infinite frequency components, meaning of that is it has infinite frequency components. Such noise is called as white noise. White noise. The meaning of white noise is it has all the frequency components. It has all the frequency components in that. We are talking this by taking noise as a signal. And noise, if it has all frequency components, it's called as white noise. Suppose if its probability density function, probability distribution, is of type Gaussian, and if the noise is additive in nature, plus if the noise is additive in nature, then we can say, or we call that noise as additive white Gaussian noise. This is very well modeled, defined noise which is used in analysis of most of the receivers even today. Right? So additive, white, okay, Gaussian model and noise. This is called as additive white Gaussian noise. Moment I say that it has all the frequency component, right? What is its power spectral density? What exactly power spectral density? Power spectral density is the plot of frequency versus square of the magnitude. Suppose if I take a noise is represented by n of omega. Suppose if we take this as omega, I can put it as n of omega magnitude square. That is going to give you power spectral density. Now, how does the power spectral density of additive white Gaussian noise looks like? It has got all the frequency components, right? Moment we say it has got all the frequency component, right? Moment we say it has got all the frequency component, we can say the power spectral density is flat like this. What is the meaning of power spectral density flat? It has got all the frequency component with this amplitude, okay, given by neta by 2, with this amplitude represented by neta by 2, which is the noise level. Sometimes in some of the textbook, this is also written as N0 by 2, noise output by 2. This is the noise. And this is the power spectral density. The power spectral density of additive white Gaussian noise. That's why it's written as SNW of omega, which represent white noise. We can put it like this: SNW of omega, which is actually the square of the amplitude of the Fourier transform of the noise signal. It's written as Sn of omega. Hope you are understanding this. Okay, so it is written as Sn of omega, which is actually the power spectral density. This is about additive white Gaussian noise. Now let us come to our focus on receivers. All of you know that a message signal m of t is modulated. A message signal is modulated and then it is transmitted. Generally this is called as a transmitter. And then you have this receiver receiving this signal, okay, receiving this signal, which we basically call as a demodulation happenings. And then definitely if it is a voice signal, it is connected to the speaker. See, this is a channel. This channel, as you all know, it can be a wired channel or it can be a wireless channel. And you know, this channel is not a clean in nature. That means there is a possibility of environmental conditions affecting your electromagnetic wave, which are transferring your signal. That means the signal transmitted through this is added with the noise. And that noise we call it as wide band noise. Name itself indicates it has got all the frequency components, or we can say additive white Gaussian noise, AWGN, or white noise, that is added to your signal here, transmitted signal here, and it is received here in the receiver. Now, what receiver has to do? Receiver has to filter out this noise component from the signal and get back your m of t. Get back your m of t as close as possible to your original signal m of t. This is a challenging task. If you look at the characteristics of a noise, your signal is completely immersed in the noise. This is what we are going to see. Now, what is the noise level? What is a noise component in various modulation scheme we have here? That is what we are going to see in this process. Now let us see, how do we receive a signal? How do you receive a signal? Normally when you receive a signal, all of you know that both in FM and AM, we use carrier signal. Your signal is modulated means your signal which was baseband in nature, this is baseband in nature. So here it is baseband in nature. Baseband means signal is low pass in nature here. Will come to the pass band. Pass band. That means all of you remember that when you see the double sideband suppressed carrier wave, this is the spectrum of the signal which is band limited to B hertz. After modulation, the spectrum of the modulated signal, it looks like this, right? It will become FC. Suppose if I take this omega, and this is omega C, and this is minus omega C. This is plus B. This is omega C plus B. This is omega C minus B. All of you know about it. See, this is the signal low pass in nature. See, this looks like a low pass filter, right? That's why we call this signal as a low pass in nature, and it's also called as baseband signal. Your message signal is baseband in nature. Similarly, your modulated signal, this is a spectrum of the double sideband suppressed carrier wave. This is passband in nature. Is it not? This looks like a band pass filter. That's why it's called as passband signal. Now this is what you are transmitted. Now when you receive this signal in the receiver, if you want to receive only this part, all of you know you have to use a band pass filter. Yes or no? You have to use band pass filter. So when you use a band pass filter in the receiver, you will be receiving only this particular part. That's why when you receive a signal here from the receiver, your signal will be a modulated signal. It can be any modulation like AM, double sideband suppressed carrier, or it can be SSB, or it can be your FM signal. While receiving, what is received to the receiver? Modulated signal plus wideband noise. We'll receive both together. This is free, like you get in the market. 1 plus 1 free. For modulated signal, this noise is free. You can't avoid it. It's inevitable. You can't say that noise you don't come. You can't say that. But it is free. Okay, it will come definitely. Now, this is the received signal now at the receiver. This is what you received at the receiver. This is signal received at the receiver. At receiver. Now I told you that I want only that band pass band signal. I want only this. Even though this is which is transmitted is mixed with the noise, I want the signal only in this range. I don't want signal in this frequency. That's why we use a band pass filter here. We use a band pass filter here. The center frequency of the band pass filter is omega C. We use a band pass filter here. And here what you get is once again same thing. We get a modulated signal plus, instead of wideband noise, this will become what type of noise? This will become band pass noise. Band pass noise. Right? Instead of this wideband noise, okay? Wideband noise, not wideband pass noise, wideband noise. Instead of wideband noise, you will get band pass noise. Right? This is what you get after this band pass filter. And the noise component, which was actually a wideband noise, okay, we call it as additive white Gaussian noise, white noise, we call it as a white noise. I have told you the meaning of white noise means it has all the frequency components. After band pass filter, which you are definitely using at the receiver, you get modulated signal, but along with that, instead of getting wideband noise, you get a band pass noise. Once again, the distribution of this, probability distribution of this is going to be Gaussian only. Only thing is that you are going to pass noise also only in that pass band region, the frequency across the carrier. Right? So this is called as band pass noise. So all of you understood now what is band pass noise. So how do you write an equation for band pass noise? Okay, so how do you write an equation for a band pass noise now? Fine. Now, to write an equation for band pass noise, let us understand the characteristics of a noise. Right? I have told you a noise is a signal, and these signals naturally we say it is sinusoid in nature. Right? These signals are sinusoid in nature. Okay. Let it be sinusoid in nature. Okay. And I have told you previously in my one of the slide by drawing a noise signal. If you see the characteristics of this noise, it has both amplitude variations and frequency variations. Yes or no? It has, if you really see this, this may have 100 amplitudes in it, or there's thousands, we say practically infinite. Similarly, it has got all the frequency components in this. So now, if you want to write an equation for a noise, especially band pass noise, that means noise occurs in and around the carrier frequency. So we can write here, okay, a noise signal as n of t is equal to, I said amplitude is varying with respect to time. So we write it as A of t. Amplitude is varying, right? Like for example, if you take the sine wave, how do you write this sine wave equation? You write amplitude, right? Suppose if you take this as am cos of omega m into t. You write like this, right? This is a single frequency sine wave. Now we are going to write an equation, a sine wave which has infinite amplitude with respect to time and also infinite frequencies in and around omega c. So we write a noise signal as equal to A of t cos. Now frequency also varying with the time, right? Frequency also varies with the time, right? That means you will have a constant frequency plus phi or theta of t. We will take theta of t. See this, see the nature of the signal. Your amplitude also varying, right? And also you see that it is also time varying with various infinite values of phase. We can say this particular signal has both amplitude variation and also here the phase variation. Phase variation means definitely it can be related to your frequency also. You know the difference relation between phase angle and the frequency. All you know about it. So this signal, what you see here is in equation for, that is n of t is equal to A of t cos of omega ct plus theta of t. So this signal is a band pass noise. The signal is band pass noise. Now this is the equation for your band pass noise, right? Suppose if I remove this omega c to some general frequency omega t, only omega t, okay, plus theta of t, this is not now band pass noise. This is an equation we can say for your white noise or wideband noise, because this omega t is now maybe in and around all the frequencies. Since we are writing it as omega ct, that means whatever changes happens, whatever frequency changes happens, it will happen in and around omega c only, within that band, within that particular band. That's why it is called as band pass noise. Band pass noise. So hope you understood now what is band pass noise, right? So now I will rewrite that equation as your band pass noise is given by n of t is equal to A of t into cos of omega ct plus theta of t. This is what we got now. Now let us do some trigonometrical simplification in this, right? So we can write cos omega ct plus theta of t. We can expand that using a formula for cos A plus B. Now I'll just expand this. So you get n of t is equal to, I'll just keep this A of t. Now you have cos A cos B, right? Cos A cos B. This is taken A, this is taken as B. So you will have cos of omega ct into cos of theta of t. Okay. Then you have sin A sin B, right? Sin A sin B. So you will have minus A of t will remain as it is. You will have sine of omega ct into sine of theta of t. Hope you are understanding this. Right? Now what we will do, see here, there are two carrier components, right? Pure carrier component. Can you tell me which are the two pure carrier components in this? Which are the two carrier components? Can you guess? The two carrier component, can you see cos omega ct, sin omega ct. This is the carrier component, right? This is the carrier component. This is your carrier signal. Right. Now we will rewrite this as, you will take a of t cos theta of t as n c of t, and we will write cos omega ct as it is. Okay. Similarly here we will keep a of t sin theta of t as n s of t, and we will keep this sin omega ct as it is. Right. Okay. Now see here. See the characteristics of these components. See, this is, you have now nc of t and ns of t are the components. Cos omega ct, sin omega ct is another component. If you see this nc of t, it is a of t into cos of theta of t. Now if you see this a of t cos theta of t, this component compared to cos omega ct, it is still a low pass in nature. This is band pass in nature. Yes or no? Carrier frequency, this omega ct and sin omega ct, right? This omega ct and sin omega ct, it is actually omega c lying somewhere in megahertz, right? It is band pass in nature. Now if we take a of t and cos theta of t, right, this is the phase variation. It is variation with respect to omega c, right? That variation is small, right? I will just show you the, just see what happens. See, this is your wideband noise, right? This is the spectrum of wideband noise, right? This is spectrum of wideband noise. I told you that this is the spectrum of wideband noise. Spectrum of wideband noise. Wideband noise. All frequency at all frequencies. You are going to pass this through a band pass filter with a center frequency omega c. Okay. If the frequency of the modulating signal, message signal, is band limited to B hertz, then cutoff frequency of this band pass filter will be omega c minus B, lower cutoff frequency omega c minus B, higher cutoff frequency omega c plus B. This is what, right? So that means what you will get at the output is a band pass noise, something like this. This is your omega c, this is your minus omega c. How this signal, which is having frequency in all components, in all the frequency, will become a band pass noise. So this is called as now band pass noise. This amplitude is neta by 2, okay? This amplitude is neta by 2. This is called as band pass noise. This is once again spectrum, okay? Band pass noise. Now see here, all the variation which is happening between in the noise, or the frequency variation which is happening, which we call it as omega c plus theta of t in the frequency, right? And this theta of t is actually happening within that B frequency only. This theta of t is equivalent to your B hertz, right? This is spectrum of noise. Okay. Now, whatever variation in frequency happens with respect to omega c, still a small, that is B hertz only. Hence, we can say this omega c plus theta of t, okay, this also omega c plus theta of t, this is just a symmetric part of this. You can see here that this variation theta of t is still equivalent to B hertz, which is low pass in nature. Right? Which is low pass in nature. That's why we are actually now telling that this NC of t, which is A of t into cos theta of t, NS of t, which is A of t sin theta of t, is low pass in nature. Low pass in nature. Okay. So I will write here this component and this component. It is low pass in nature. That means it is band limited to B hertz only. Whatever frequency variation happening in band pass noise is omega c plus B and omega c minus B. That's what we are actually modeling it here as omega c plus theta of t. This is theta of t plus theta of t, omega c minus theta of t. And this theta of t is actually here in this case is B hertz only. Right? So we can say the component A of t into cos theta of t is low pass in nature and band limited to B hertz, which is actually the maximum frequency of the message signal. Sometimes instead of B hertz in the note which I have given you, you may have it as omega m. Okay, omega m. Sometimes it will be written in the radians per second. Okay, so that's why instead of B I will write omega m here. That is going to match better here. Okay, omega m. Okay, instead of writing here omega c plus minus B, I will write omega m. I will write omega m here. That better suits here because we are writing in terms of radians per second. Have you understood this now? Right? Have you understood why this NC of t and NS of t is low pass in nature? Because of A of t cos theta of t. Hope all of you understood about this band pass noise. Okay. Now, once again, let us see this is what noise. Now if you see this, if you see both NC of t and NS of t, okay, those are identical. Those are identical. Right? A of t cos theta of t, A of t sin theta of t identical. That means if you take the root mean square value of this NC of t, NS of t and N of t, okay, the root mean square are going to be identical. That means the power, if you see the power of this band pass noise, okay, if you take the power of the band pass noise, see here you have N of t is a noise, right? Is a band pass noise. We have seen it. Okay. And NC of t, it's called as in phase component. Okay. And similarly NS of t is called as quadrature component. In this, there's a name given to this. So this NC of t is called as in phase component. Okay, I will write it somewhere here. In phase component. And this is called as quadrature phase component. So these, if you see the power in this noise and in phase component and quadrature phase components are same. It's identical. So we can write mean square value of noise is equal to mean square value of this in phase component equal to mean square value of the quadrature component. Right? So that means both NC and NS of t both have identical power spectral density. Right? I think all of you know about power spectral density. I am repeating once again. Power spectral density is a plot of a frequency, okay, and your y-axis is square of the, suppose if you take a signal m of t corresponding Fourier transform is m of omega. Suppose if you have a signal corresponding Fourier transform of omega, if you take a square of this, okay, take the magnitude and square of this, and whatever plot you get, and this is the plot which is power spectral density, something to do with the power with respect to frequency. That's why here we say the power spectral density of the noise, power spectral density of the in-phase component, and power spectral density of quadrature phase component is same. They have same power spectral density. Okay, now let the power spectral density of a band pass noise n of t, okay, the power spectral density of noise n of t, okay, this be s n of omega. I will write both the arrow like this. This is transform pairs. I told you that this is also equal to power spectral density of the quadrature components, power spectral density of the in-phase component equal to power spectral density of the quadrature phase component, which is nothing but, we can write it as Sn of omega minus omega c plus Sn of omega plus omega c, okay, for all the value of omega, okay, less than equal to omega m, yes or no, and it is 0 elsewhere, right? That's what I have drawn here. See, this is equal to, this is your S1 of omega, this is omega, right? So you have this signal Sn of omega, Sn of omega minus omega c, Sn of, this is what actually your this is called as band pass noise power spectral density of the band pass noise n of t. And I told you that all the value of omega, see this omega, you have this omega minus omega c, omega plus omega c, and this omega value is actually less than equal to omega m, and this magnitude value less than omega m. That means here you have omega c, plus omega m, and this is omega c minus omega m. And it is 0 elsewhere. See, it is 0 elsewhere. Everywhere it is 0. Can you see here? This is actually called as power spectral density of the band pass noise. Okay. And one more property of this nc of t and ns of t. Okay. We have this in-phase component and quadrature phase component of the noise. Now this is uncorrelated. The correlation between these are 0. That means if we take the expected value, this is something to do with correlation, cross correlation, right? So the cross correlation of this signal, that is expected value of this equal to 0. The same expected value which you use in the random process. Right? Hope you understood about this noise. Okay, what happens when it passes through the band pass filter. Okay, so everything is, hope it is clear for you. Right? So in general, depending on whatever cos or sine you take, okay, your n of t can be written in a generic way as NC of T. Your noise band pass noise can be written as NC of T cos of omega Ct plus or minus Ns of T into sine of omega C into T. See here we have started with N of T is equal to A of T cos omega Ct, right? It can be N of T is equal to A of T into sine omega Ct plus theta of T, right? So both can be possible. That's why, and from both equations this can be derived, and we have this equation as a generic equation. Right? So once again I'm just telling you white noise has a power spectral density which is flat. This is the power spectral density of the white noise, which I will write it as SNW of omega, and this amplitude is theta by 2. Sometimes it is written as N0 by 2, this amplitude, and this is frequency. All frequencies, see here, all frequencies exist, that's why it's flat, right? See, if it is a low pass signal, only low frequency exists. This, if the power spectral density is like this, okay, that means only this much frequency exists. See, only this amplitude exists, all this doesn't exist. But this particular power spectral density, which is the power spectral density of the noise, white noise, full flat from all frequency, omega from minus infinity to plus infinity, it's flat because it has all the frequency components. That's why it is called as white noise. So this lecture is exclusively to tell you about the noise, right? Band pass noise, especially band pass noise. So why we consider band pass noise? Because in the receiver, first you use band pass filter. Noise also filtered, right? Noise also filtered. That's why we consider only pass band noise, right? So this lecture is actually only for noise. You watch this video, repeatedly watch it if you're not understanding. Next lecture I will post on noise in baseband system. Now we have seen noise in passband system, right? Right? Okay. Now what is the noise in baseband system? Suppose you have a signal m of t, your signal m of t, that's your message signal, which is low pass in nature. We call it as a baseband signal. We call it, we'll actually pass it through a low pass filter. Okay, we'll not do any modulation, right? We just simply receive that, and without making a modulated signal, we'll receive low pass signal only, and we'll add the noise to that. Okay, and then we'll see what happens at the output. Okay, that's what going to be your next lecture. So I don't want to make this lecture very big. Maybe next video you will be able to see that is a noise in the baseband system. Okay.